ହଁ, ସେ ଭଲ ଥିଲେ।
All right, so we'll start. Uh, and again, this meeting is seem to be scheduled for 1 hour. So if it gets over in 1 hour, then I'll, as like last time, I'll put the link for the next meeting, and then you can join in that. So yeah, okay, you were asking about DGPS process. You mean the differential global positioning system, that one? I assume that you are asking about the differential global positioning system. I just know a basic idea of that. Like I'm not very well versed in it, but if possible, I can maybe give you more details in the upcoming session. Like basically, it is a technique which is used to improve the accuracy of GPS positioning. Like for instance, you know that in different places, across the globe, we have GPS stations. So that for this location thing and all in Google Map and everything, so that actually utilizes this GPS data. So for that purpose, at times what happens is this atmospheric disturbances, like cloudy, something like that, or sometimes even the satellite and the receiver might not be like aligned properly, like the time of receiving the data, such things, like several factors are there which can affect the GPS position that is being determined by the base station. So in such situations, in order to account for those errors, you need accurate data. So to some extent, when you need the proper data, then what you have to do is this differential GPS system is used. So what they do is they improve the accuracy of GPS positioning by correcting the errors, which is, as I said, which is caused by this atmospheric disturbance or other factors like this satellite clock drift, such things. So basically, it enhances the precision of GPS data. Like, uh, y- like you will get like if it's just a random thing, like you don't need a very accurate uh, position and you just need a random location, then the normal GPS would work. But if you're very particular about where exactly that point you're looking for is, then in such situation you have to make use of differential GPS system. Uh, that is what, and I think its precision is also really high compared to the normal one. Like I read somewhere that it's mm, like meter to centimeter range also. It's very precise. So that's the basic thing I know. But if it's something that interests you, then if we have time, maybe we can discuss it later. Okay. So I'll start with today's session. And before I begin, I just want to say I the PPT that I had prepared, some problem came, so not all the slides I had added was there. So in between, I will switch to Professor Saraf's slide also, so that it's easier for me to complete it. So yeah, I'll share the screen and let's begin. I hope the screen is visible to you. Okay, so we'll start the week 6 discussion. So once again, welcome to the course Geographic Information System, uh, which is taken by instructor Professor A.K. Saraf, and I'm the teaching assistant Anshana. So yeah, welcome to week 6 discussion session for the course, and we'll be mainly focusing on the network analysis part and the remaining, I think another topic Sir had begun at the end of this session, which I think it's better if I take along with the week 7. So I'll not be focusing on that. I'll be focusing on the network analysis part and the attribute classification part mainly. And that to just summarize the topic so that it refreshes your memory. Okay, so let me just fix my pen. So, as in the initial classes also, Sir has said, and then basically by now you might understand that the analysis part of GIS, that is basically the heart of GIS. Like you collect data, you determine what data you need, you combine them, and then when you analyze that, that is when actually you're doing something with that data set, right? So analysis is a key part of GIS, and a user, like the person who is using this data set and doing the analysis, they must spend a lot of time on this analysis in order to get a good output, and also like proper modeling, and even at times people use it for prediction, things like that. So for this purpose, the user has to be very careful, and also spend a lot of time in the analysis part. Like as I said, like at times when you are, for instance, like last class we were talking about intersection, merging, all those things. So certain factors are very much user defined. Like the user need to decide what kind of data needs to be taken, what needs to be negated, all those things. So as I like the gist of this is that analysis is a very important part of GIS, and the user has to spend a quality time on that in order to get a good output, a good modeling. Okay. So in this lecture, as I said, we'll be first focusing on the network analysis part. So GIS is like recently, especially, it's extensively used for network related applications. Like for instance, like as I was saying, in transport system, okay, so or in this electricity, the power transmission, those things. So it's like that networking is very important, like road networks, pipe network, like connectivity is important. I am not sure if you're familiar, like for instance, water supply network. So that has to be very well planned so that it reaches the people that they have intended to. Even the traffic, like recently, if you take a look at it, almost every person, every home, there is at least a car or a scooter at least. So they have some sort of vehicle with them, which means the density of vehicles on the road has increased. So in order to, you know, mm, understand the traffic and then regulate the road network accordingly. So for all those purposes, I'm just basically telling you why this is very much necessary, especially in the present time. So this network in data sets, they are made up of network elements. Okay, so network elements are generated from the source features, like whatever vector data that you're getting, like the point data, line data, or even the polygon data. Now that elements are created from this vector data, and then that elements are used to generate the or create the network data sets. So basically, what are these elements that we're talking about? Okay, so that we need to understand. I think, okay, yeah. So the main three kinds. So you have to remember, like that what, like if you're asked what are the three kinds of network elements or how many network elements are there. So the answer is three. And what are those? We have edges, we have junctions, and we have turns. So edges will connect to other elements and are the links over which agents travel. And junctions, they connect edges and facilitate navigation from one edge to another. And turns, they store information that can affect movement between two or more edges. Like I think I have an example, so maybe that will help you understand this better. So just a minute. Edges and junctions, they form the basic structure of any network. Okay. So connectivity in a network deals with connecting edges and junctions to each other. Like you have to remember, network is basically some sort of connection is happening. Okay. So that connectivity is maintained by the connecting edges and junctions to each other. Turns are optional elements that store information about a edge movement. For instance, a left turn is restricted from one edge to the another. I think I can show you an image or something. Let me just check. I had kept an image, but I don't know what happened. So maybe I'll just try to obtain another one. I can't find it. Anyway, like a real life example, in that sense, if I talk about this, like edges basically represent the linear features, like right here. So edges, they represent the linear features, okay? So linear, what are the linear features? We have roads, we have pathways, or even the pipelines that I was talking about, water or gas pipelines, whatever it is. Okay, these are edge features. They are basically linear features. Now they connect two junctions. Junctions are basically the nodes. So if you remember when we were talking about vector data and all, so we had these polylines or something like that, and we called these as edge nodes, and then I think this was the internode or something like that. Anyway, this connecting points, no, they are called as junctions. Okay, so they connect, the edges connect two junctions or nodes basically. So this is the edge, and that is connecting two nodes or junctions. And they have attributes like length, direction, all like such like in the attribute table, when you can even talk about their length or the direction that they are in, or at times if you're talking in the time aspect, you can even talk about the travel time. Need not go into that much detail. Now they can be directed like in one way street, or they can be undirected like bidirectional roads, okay, one way road, or like two way, whatever it is. So a good example of edge element is a street network where each road segment is an edge. Okay. Then we have junctions. So junctions are also called as nodes. They are the points, as I said, where two or more edges meet. Okay. So these represent the intersection endpoints or network connections. So for example, in the road, a road is a very good example for network analysis. So you can always think in this aspect, like whenever I'm saying some example, think it in terms of roads. So basically what you have to understand is they are basically the intersection. So for example, if you have a road coming this way, you have another road coming this way, and then this is going like this. So this is an intersection. Okay. So they represent the intersection, even the end point also they can represent, or the network connections. Like this might be an endpoint, or the connection can also come. So whatever it is, it's basically a node. Okay. It can be simple, it can be complex also. Then, as for turns, so turns are not very mandatory elements in network elements, but then, uh, like it's better that you know that. So turns, they define restrictions or costs when moving between edges at a junction. So it's basically a good example is for example, you have turn restrictions, like certain roads, they say that you should not enter, certain place, they say that you should not go to left, or sometimes they inform you that there are sharp turns ahead. So such things, they basically define such restrictions, turns. Okay. So the importance is that edges will determine the connectivity and cost, like shortest path, the fastest route. So for example, if you take, you want to see how to reach a particular place, then at times Google Map also shows you which is the shortest distance, which is the longest route, or in which route the traffic is less, such things. So there the edges comes into play. Junctions, they define where movement is possible or restricted. uh, that kind of information is given by junctions, and turns will help you improve accuracy by considering real world constraints. So then we have network sources. So there are three types of network sources. Uh, just a minute. So just like how you have three elements, so you also have network sources. So there are three types of network sources that can contribute in the creation of a network data set. So we have the edge feature sources, then we have the junction feature sources, then we have the turn feature sources. Mm. Okay, so the edge feature sources, they line feature classes contribute as edge feature sources, just like I was saying. Then the junction feature sources, basically the point feature classes contribute as junction feature sources, and the turn feature classes contribute as turn feature sources in a network. A turn feature source explicitly models a subset of possible transitions between edge elements during navigation. So it's basically, you talk about elements and then sources, so it's more or less the same thing. Edge is a line feature, junction is a point feature, turn feature is an optional one, which tells you like the restrictions that might be present when you uh, use the edge or the turn feature source. I mean the junction feature source. So each feature class that contributes in a network as a source generates elements based on its assigned role. So for example, a line feature class is used as a source for edge elements, and a point feature class is used to generate junction elements. Just the same thing that I said. Like every time that you talk about edge sources or edge elements, it's always related to a linear feature or a line feature. And every time you talk about a junction element or a junction source, you are talking about a point feature or a node for that matter. So in network analysis, like whenever you're doing network analysis using these elements and all, you need to mainly consider the four components. Okay. So here, what you have to bear in mind is this. Network analysis, four components are usually considered. So one is a set of resources. A good example that they've given is based on the river system. So the set of resources is the sediments that are transported by water, the location of resources, that is the fluvial system, obviously the river system, a destination where the outlet of the watershed is present, and a set of constraints like only permanent streams of higher order, like such things. So it's basically the resource, like what you want is the sediments which is transported by the water, and that water or whatever sediments is there, that is obtained from what? You get it from a fluvial system. Then you need to know where the destination is. So where that watershed or where that fluvial system's outlet is present, that is where you can actually obtain this sediments. Then you also have to consider certain constraints, because a fluvial system is not just a linear, like a single path one, it has several uh, networks. So you have to set some constraints, like you will only consider the streams which are of higher order, and that too permanent streams, because certain streams might be very seasonal, like only when rain is coming, only that time that stream might be active, such things. So this is like based on the example, we are talking about the four components in a network analysis. So here you just have to remember the resources. When you talk about resource, it is the sediments and even water itself. Then we had, like Sarah discussed this diagram. So this is a street network basically. So this network has a street feature class that can act as an edge source. So streets are there, no? So this lines that are shown here, so they behave as edge source. Okay. So there might be a rail station, there might be a metro station, several such networks may be there along with the power network, whatever it is. So in this street example, like the streets are the edge source and the intersection, the like street. Mm, okay, I thought somebody has joined. Okay, anyway. So the street features, they represent the edge source. The intersections, street intersections, they represent the junction source in a like when you classify it as network sources. So edge source is the street, the junction source is the street intersection. And then the third, the additional line feature class as and the edges in the rail lines might be there. So here you have the street intersection, you have the street edge sources, but additional edge source can be this rail line also, because that is also an example of edge source. Okay, that can also be there, or bus route if they have indicated that one can be an edge feature. Then the point feature classes that act as junction, like in uh, just a second, I'll in case of rail stations and in the bus stations, these junctions, intersection points. Then all feature classes that reside in the feature dataset, which contains the network dataset, can participate as network sources. So whatever feature classes are present, it can be because we are talking about edges mainly. So it can be, as I said, streets, roadways, the rail network, bus route, pipeline, whatever it is. So they can all participate as network sources. Only two sources can participate in a shapefile network dataset, like a line shapefile and a shapefile turned feature class. So like you, okay, now I have to open the other one. Just a minute. Before I share the other page, I'll share the link for the next meeting so that it's easier for you. Just a minute. Let me just generate the meeting link and then I'll share it here. Okay, so I have shared the link, and when this meeting ends, so I'll start that one and then we can continue. Okay, so I'll share the files that I had downloaded. I hope the screen is visible, so I'll show that. Yeah. So from here, I have
Yes,
to. I had.
yes, yes, ma'am, visible.
Yeah. Okay. Thank you. I had included this in the PPT, but I am not sure why it didn't. I forgot to save it, I think, so it's not present. So yeah, we'll go with this. Okay, so in network analysis, sir also talked about system junctions. So we'll go to that. There are system junctions which exist at each end of edge in a network dataset. So as I said, it is the nodes or the connecting points. So wherever these things are there will be a junction or a terminus also, like you can say it in that way. So if a junction source a feature is not created at the end of an edge, that means a polyline feature, like in a polyline feature, a system junction can be created automatically when the new network dataset is built. Okay, so system junctions are stored as points in a source feature class, which is automatically generated during the first build operation. So, uh, like in this GIS platforms like the ArcGIS or the QGIS, like at times when you create this line feature, like you are given a map and then you have to create the vector data set from that. Like you have to use points, lines, and polygons. So, if you are using the polyline feature, so most of the time what happens is that you click in, okay, I can't show it like this. So like basically you click at one point, then the next, then the next. So, and like if you don't, I'm not very sure how it was done in ArcGIS, but in QGIS, like I think you have to right click or something or double click. Only then will that point line feature terminate, and then you can start with the next one. So the source feature class will be named as whatever the network name is and underscored junctions, where network name will represent the network dataset, like what kind of element that has been used. So when a network dataset is created, like for instance, if it is a power supply network, again it is going to be different for edges and junction elements. So we have to ensure that edges and junctions are created or formed correctly, because when we run the optimization or whatever it is, it should work properly. So that's why I was saying, like, it's very user specific. If you are not very clear about what all networks you have to create or what all points you have to consider, if that is not done properly, then the analysis itself will not be fruitful. So ensuring that edges and junctions are formed correctly is important for accurate network analysis results. So connectivity in a network dataset is based on the geometric coincidence of line endpoints, line vertices, and points, and applying connectivity rules that you set as properties of the network dataset. So for example, what I'm trying to say here is, I'll try to write here. It's not. What I was trying to say is like, uh, these uh, edges and junctions that I was talking about. So whenever you have, for instance, let's say you have a map and like the one that was shown before, for example, like this. Okay, so you have a map like this, and then here you have to identify these points very correctly, like where that intersection is coming, where the line is ending. So in that aspect only you can actually define all these things, network elements, in a GIS software. Only then, like if you have for instance, if you had forgotten to add this junction and you just you just drew a polyline straight away, so then that is going to affect the analysis because there is a junction present here but you did not include it while marking it. So you have to be very careful when you're taking care of the connectivity. So the connectivity in network analysis begins with the definition of connectivity groups. So each edge source is assigned to exactly one connectivity group, and each junction source can be assigned to one or more connectivity groups. The reason is that like the junctions, it can be associated with uh, probably two edge sources, right? But one edge source will mostly have one connectivity group. So a connectivity group can contain any number of sources. So here, if you see, uh, so here you have a metro line that is present, and then you have a uh, what is this is better. Okay. So here they have represented the metro line, street, and the metro entrance. Okay, so different colored lines are here. The streets and the entrance, all those things have been marked here. So all these things like the metro line, the street, and the metro entrance, they are all interconnected. So we consider them as a group. Now in this, the street and the metro entrance can come in one group because they are related in that sense. And the metro line and metro entrance are also connected. But then metro line and the street is not directly connected because how the metro line goes is not that uh, decided by the street, but then the street and the metro entrances have a connection. So I'm just picking up certain slides only because we do not have that much of time and I don't want to repeat whatever is there. So how these edges are connected? So here edges in the same connectivity group can be made to connect in two ways. Okay. So here the first one by set of connectivity, like if one set of endpoints connectivity, the line feature becomes edge joining only the coincident point. Like here you can see you have one line here, another line here. Now if we can name the junction, so here junction 1 is there, junction 2 is there, junction 3 is there, junction 4 is there, and the edges are 1 and 2. Okay, so edges in the same connectivity group can be made to connect in two ways set by the connectivity policy on the edge source. So if one set edge endpoint connectivity, line features become edges joining only at coincident endpoints. So in this particular case, line feature L1 becomes edge element E1 and line feature L2 becomes edge element E2. There will always be one edge element created for one line feature with this connectivity policy. So you have two line features and you have transformed them in terms of edges and junctions. So this is an example related to bridge. So here there is one bridge and there is another bridge. So that like one is going like this and there is another, but they are not actually there is no connection that is existing between them. So when that connection is not there, then it might be a bit difficult. So the bridges source is assigned endpoint connectivity, and these are created by using endpoints. Like here you can see like there are two bridges, but actually it's like one over the other. So there's no basic common point for here. There is no connection here. So only the end points are connecting them. There is no midpoint or the intersection that is present. So if users set any vertex connectivity, line features are split into multiple edges at coincident vertices. So what exactly is explained here is we have the same line L1 and L2. So two polylines are crossing at a shared vertex point position are split into four edges. Earlier, if you remember the example, we had two edges and four these points. Okay, we didn't have this vertex over here. But in this example, we have a connection like this. So instead of two lines or two edges, we have here four edges with a junction at the vertex. So edges E1 and E3, if you take a look at this, E1 and E3, they are identified with source feature class and an object ID of line feature L1. So it's kind of like in mathematics, they say set and subset, right? So the main thing is L1, and then E1 and E3 are kind of like they belong to the L1 group, but then they are the split form of L1. The edges E2 and E4, if you take a look at that, they are identified with the source feature class and object ID of line feature L2. So basically what we are trying to convey here is that when you do such things in a map, like you involve a vertex or a point between two lines or something like that, and then when you get that in the attribute table, then you have this E1, E3, E2, E4, they will come under their respective line feature. The junction J3, which was introduced here, will be a newly created system junction. So junctions J1, J2, J4 and J5 will either be system junctions or junctions from coincident points from a source feature class. This J3 is a newly introduced one, but J1, J2, J4 and J5, they are like whatever that initial points were marked, they will be a part of that one. Not all crossing line features can produce connected edges. If these do not share any coincident endpoints or vertices, no connectivity policy will create a junction at the point of intersection. So here, if you take a look at this, like that's kind of the same example we were discussing. So here, E1 is in one direction, E2 is there, but they are not having any kind of vertex. They are not connected in any way. So street data for network datasets must be cleaned first so that either vertices or endpoints are present at all intended junctions. That's what I was trying to say. Like if you have a street data, you need to make sure where all these intersections are or where these turns are or where these common points are. Only then can you actually generate a proper, like you do a proper network analysis and thereby generate a proper network model. So to overcome such street data, either use a geoprocessing tool like Integrate to split crossing lines or establish a topology on these feature classes and edit street features while applying topology rules that enforce feature splits at intersection. That is like I have not done it personally, so I don't know very well, but what I understand from this is that in certain cases, like when you're dealing with a huge data set or a big map or something like that, at times you might have to use such geoprocessing tools like Integrate in order to split the crossing lines. Like you might find such crossing lines in multiple positions and you might not be able to do it manually. So you can use such geoprocessing tools which will take care of that and introduce a vertex. So edges in different connectivity groups can be connected only through a junction shared by both connectivity groups. Okay, so you have edges, like you have different connectivity groups. There are different edges also present. Now, two edges that belong to different connectivity groups, they can only be connected by a junction. So, in this example uh, of a multimodal system combining a bus network and street network, okay, you have a bus network and a street network. A bus stop is added from a point source and is in both connectivity groups. The point location of the bus stop must then be spatially coincident with the bus lines and street lines it joins. So the basic thing is like you have two lines, they don't basically have any connection, but then when a bus stop is added, they are connected. So in this, these points are connected, but these two are not. Only thing you have to bear in mind, like there are so many examples that are given, but only thing that you have to keep in mind is that what are the network elements? You know that edges are there, junctions are there, turns are there. What are basically edges? They are linear features. What are junctions? They are basically point features like nodes and all. And then you have to understand that two edges, they are connected by a junction. Turn is more of an optional element, and that's why we have not discussed it as much. So when the point location for the bus stop is added, whether it successfully becomes a junction depends on the junction connectivity policy. As with edges, junctions connect to edges at endpoints or vertices depending on the target edge source's connectivity policy. However, there are situations in which you might want to override this behavior. So that's basically like at times certain programming is already done in order to introduce such junctions or points. But there are certain situations where you might not require such corrections. So you might have to override that processing and then you have to given information as to not do it. Then there was this attribute classification methods were discussed. So basically, humans use categories in every aspect of everyday life to make sense of the world. Like, what are these categories? As I was like from the beginning, I was giving this example. Like, if you have an India map, uh, it has country boundaries, like that administrative boundaries present, the district boundaries are there, and if you go much in detail, maybe the city boundaries or village boundaries, whatever it is. So all those aspects are kept in the attribute table, and then based on your requirement you can select it or deselect it and then use the file accordingly. So in the classification, basically like classification is the process of organizing data into group or categories according to shared qualities or characteristics. So you have a bulk of data, and those data sets which are similar to each other, you classify them together, right? Like for instance, in the dem model elevation, like slope, we that classification, we if you remember we had discussed that example. Like dem model has all these information regarding the slope, the elevation, the depressions that are present, all those things. But if you classify a dem model based on the slope at like in an interval of 50 meter, I think the meeting is going to end soon. It's showing a prompt over here. I'm not sure if, let me just see how much time is left. Okay, it's showing the call will end in 9 minutes. So maybe just 1 or 2 minutes before that, I'll end the call and I'll start the next meeting. So that I think that would be better. So as I was saying, so if I have a digital elevation model which is showing a continuous elevation for a terrain or something, and I want to create a classification that, like for instance, I want to create a relief map. Relief means the different heights and all those things. That is more easier for or understandable for somebody who is using that DEM model for some basic purpose. Like you don't need all the information that is present, you just need the relief information. So accordingly, that is the reason why we do classification. Now classification is used in GIS, cartography and remote sensing to generalize the complexity in geospatial data. Geospatial data might be very complex and very uh, intense for somebody who doesn't need that much of information. So classification helps you in simplifying that. There are 6 classification methods which are commonly used in GIS. Like in order to simplify the data set, we use these 6 classification methods. So the first one is equal interval. Then you have natural breaks or jenks, quantile, equal area, standard deviations, geometrical interval, all these things. Okay. So classification method changes a continuous data theme to discrete classes. Example image was also shown in the previous class. So okay. So the purpose of classification is twofold: to make the process of reading and understanding a map easier, and to show something about the area which is being studied that is not self-evident. Like for instance, you are looking at an area, you might not get an information just by observing that area uh, firsthand, but then when you use a model or something like that, you get some more information which might not be visible to the naked eye. So first classification, as mentioned, was equal interval. So the equal interval method, it divides the range of attribute values into equal sized sub-ranges. Then the features are classified based on those sub-ranges. Okay. So what it so here at the top you can see, I'll use my mouse better. Yeah. So here at the top, you can see a digital elevation model, right? And then it has been categorized into 3 equal sized subcategories or categories having different elevation ranges. So here it's a little more complex. You are not able to differentiate too many aspects, but here you can see that it is simplified into 3. So this might have been done based on some elevation thing. Like this might be the tallest point, then as you go from here to here, the elevation is decreasing. So this is a very simplified thing. So it's more or less you're assigning some intervals and then you're getting an output which is very simplified. Then we have the natural breaks or junks. Okay, this is based on Jenks optimization or Jenks formula, and basically this method identifies the breakpoints or a sufficient or large gap in the data which is based on statistical formula. So instead of you just directly assigning something, in case of this Jenks or natural breaks, some statistical formula is used in order to identify large gaps that are present or breakpoints that are present, and it is a bit complex than the equal interval method, but basically what it does is it minimizes the sum of variance within each of the classes. Like it will not, as I said, classification is done in order to reduce the complexity. So whatever variation is happening between these classes or within the classes, that will be minimized so that it's easier to understand. Then we have the quantile classification method. So in this method, each class contains the same number of features. So that same elevation model has been taken here, which we had seen in equal interval. So in the output, you are having different classes, and these classes are basically frequency based classification. So what it means is each class is having same number of cells or pixels in it. Like if you remember in the previous image, this was smaller, and then the next, like we had 3 classes, and it was based on some elevation differences. That's it. But here, this is mainly based on the fact that each of the class has same number of uh, cells or pixels in it. So one other thing that you have to bear in mind is like you have several classification methods. So it's you who has to decide like which classification method is better for which kind of like the kind of data set that you're handling. So what I'm trying to say is like for example, in case of population count, it's usually not suitable to do the classification with quantile. Only few places are highly populated. It's not uniform, right? So if you're having a surface which is representing the population counts, and that is already having some concentration of population or high density of population, then this will not be very useful, because this is kind of like how do I say that, making it uniform across different classes. Like according to quantile classification, each of the class will have the same number of pixels or cells present. But if you're taking into consideration the population of an area or something like that, you have to understand that certain areas might have more population compared to the other side. So if you take into consideration the quantile classification, that aspect will not be accounted for. So as a result, in population count, you may not be able to use the quantile classification. So in this case, the number of classes might have to be increased, which actually in effect uh, makes the data complex and not simple. So quantiles are best suited for data that is linearly distributed. Then we have the equal area classification. So this method classifies polygon features by finding breakpoints so that the total area of the polygons in each class is approximately the same. So, uh, so this is the fourth method that we are discussing, and it's basically you can apply this on the raster data by finding the breakpoints. Classes determined with the equal area method are typically very similar to quantile classes when the sizes of all features are roughly the same. Equal area will differ from quantile if the features are of vastly different areas. So it's like it's more or less similar to quantile classification, but in case of equal area classification, our main purpose is just to like however you find the breakpoint, that doesn't matter. You find several breakpoints, you generate several polygons. Ultimate thing is all the polygons will have the same area, irrespective of the shape that it is in. So in quantile also we are using frequency of occurrences of individual cell values. Now equal area will differ from quantile on one account that the features are vastly of vastly different areas. Okay, equal area has equal, like basically polygons have equal area. Quantile, it may not have the same area, but it might have the same number of, not may not may, but it will have the same number of pixels or cells. Then we have the standard deviation classification. So this is the fifth one, which is a purely statistical based technique of classification. So in this, the mean value is found first, and then class breaks above. Yeah. So this is a classification scheme where the class breaks are based on class intervals that have a geometrical series. So these are like that quantile. Like if you take a look at the image that has been generated in the output, they're like quantile, but there's a slight variation to the equal area. So as I was saying, like quantile and equal area appears to be similar, but the difference is that in quantile it may not have the same area, but rather it has more or less like similar number of cells and pixels. But in case of equal area, like whatever polygons you generate, whatever shapes they are in, ultimately you have the same area. Now this classification scheme, that is the geometric interval, it's a slight variation to the equal area. So similarly, it is also the class breaks are placed on class intervals that have a geometrical series. Like in this left image that you can see, this is the original input digital elevation model that was also shown before. And by doing this geometrical classification, we get output which is similar to the ones that we have seen before, but it's not exactly the same. So Sir had also introduced this. So basically this classification is done based on this geometric series. It's a little mathematical and I'm not very well versed in this. So if further explanation is required, then I'll just go through the material and then maybe I can do that. So the geometric coefficient in this classifier can change once to optimize the class ranges. So it's like purely a mathematical classification that is being used here. So this is how all these classifications have been used in a particular scenario. This is an example. This is not from continuous data, but it is from a vector data. So what you see here is the same data set has been classified using equal interval, quantile, natural breaks or Jenks, geometrical interval, and standard deviation. So here, if you take a look at this, the number of classes that has been generated here is 5 in all these first 4 ones, like equal, quantile, natural, and geometrical. But when you come to standard deviation, you have 7 classes. So if you take a look at equal interval, this may not give us very good results in this particular case. Like this is population thing, no? So it's not very good population against each land record and is having equal interval like 3 to 6, 6 to 9, 9 to 12, 12 to 15. Like a 3% difference has been maintained here. But when the same data set, like this percent population, when you're doing it in quantile, uh, or even in natural breaks for that matter, so here you do not have an equal interval. It's like 2.7 to 6.3, then like 6.3 to 6.8. So the interval is not the same. Here also 3 to 6, 6 to 7 like that. So it's more or less, it takes into account the population density also. It's not, the main purpose is not to divide it into equal intervals. The purpose is to identify the places according to the population density. So So if you take a look at this, I think the quantile is giving you a more better result, as you can see here, when compared to, definitely when compared to equal interval, and then maybe after that you can consider the natural breaks or jinx to give a better accounted population percent data. Now when you compare this with the geometrical interval or geometric method, you can see 5 classes are there, but it is again giving a different result as compared to all these 3. Like here you have certain common classification things if you focus on that, but a better classification is given by quantile. So this is why like Sir has also repeatedly said, and like based on like somebody who is using GIS for analysis and modeling, so different classification methods on the same data set, like all these methods are using the same data set, but they are giving you different results. So the results are basically depending on the distribution of the data and statistics of the data. And it's more mainly like dependent on what kind of data you're using and what kind of classification you require. That's why even while we were discussing equal interval, like sir has also mentioned that if equal interval might be good in a different aspect, but when you're considering population or population density, that is not a good classification to go ahead with. Then we have manual classification that is done to emphasize a particular range of values, such as that above or below a threshold value. So, like you keep a threshold value, a maximum limit or something, and then above that, whatever classes are there, and below that, whatever are there. So, it's something like density slicing, which we had talked about. Uh, and that is mainly, since it is manual classification, it is primarily influenced by the user. So, sir has given an example in this with regard to one may want to emphasize areas below a certain elevation level that are susceptible to flooding. So, for instance, if you consider the Himalayas, so most of the time the flooding is contributed by snow melt also. So, for a GIS user, like I just want to see only those areas where snowfall is happening. So if I know that roughly around like 2000 meter and above snow is present, then I will mask everything that is below this 2000 meter elevation and will only take those data sets which are above 2000 and above. So here we have a elevation model DEM over here, but then I simplified it in such a way that I'm only considering that area which is above 2000 and below 2000, nothing in between. So based on this, the people evacuation at the time of flooding, all that can be facilitated. So this is very like dependent on the user. Uh, Unlike other classification, which is also dependent on the statistical aspect or the mathematical aspect. Here it is mainly the user is defining like, okay, I know that below 2000 meter, the risk of flooding is more. So it's better that I identify the regions which are above 2000 meter for ease of people evacuation during the time of a flood or something like that. So through this manual classification, our ultimate aim is to emphasize the areas below certain elevation levels that are susceptible to flooding or which are safe to take people away from such areas. So here an equal rural houses based on equal interval method has been done. It's a very simple and straightforward one. So in this classification, the rural house percentage has been considered. And assuming that houses in rural areas in India are not very, like the recent well-built houses. So they may be just made from mud or other things like stone and such things. Like facilities might be very less. So such rural houses will be more susceptible to events or natural disasters like earthquake. Okay, so one example that sir has mentioned was the earthquake in Latur about like 30 years back. And at that time, it's like such houses, like such rural houses were deeply affected because they did not have the built to withstand. I'm not able to hear anything if anyone is speaking. Oh, I'm really sorry, like my mic was on mute. I didn't notice that. Okay, so what I was saying is this is an example of district classification based on rural houses percentage. So here you can see that this classification is like equal interval classification. So here you have rural houses classified from 0 to 10, 10 to 20, 20 to 30. So what they mean by this rural house, like what they're trying to imply by that is that this kacha houses, pakka houses, that classification is there, right? The ones which are made from cement and like concrete, iron bars, and all those things. So, unlike that, rural houses are mostly made by muds and stones. So, in the event of, let's say, some natural disaster like an earthquake, such houses might be more susceptible to uh, damage or maybe total destruction. So when you make such classifications and you understand like which area is more susceptible to damage, such things you can do by making this classification. So the example that sir had given was the earthquake that happened like around 30 years back in Latur. So they mainly had like if you take a look at this color, so that's like 70 to 80% of that region had like 70 to 80% rural houses were present in that area in Latur. So what happened was a large number of people died because they like because these houses does not withstand such an event, and like if the basic thing is earthquakes as such don't kill any people. Earthquake is basically the earth is shaking, but then death happens when they are not protected, when certain things fall over them or anything like that. Like if people are standing very close to the building fall on them, then death happens. If they are in a building which is not at all safe during an earthquake and it collapses, that is when death or injury happens. So that is what you have to bear in mind. So, like basically, what I'm trying to convey is, if even if you have a very high magnitude earthquake that is happening, but you are staying in a place where there is nothing to fall on top of you, like you are staying in a very open ground, and there is no big buildings nearby or any structure that can collapse on top of you, then you will only experience that shaking and nothing more. Not there is the chance of casualty is very less. But then, even if it is a medium, moderate magnitude earthquake, but you're staying in a place which is not at all safe, like the example that is given here, like rural houses, and are like you're staying in a rural house or something, then the risk is more. So if you're inside a kacha house, like a rural house, even a 6 magnitude earthquake can damage the house and it can end up being life threatening. So this and a next map was given an example of Jabalpur in Madhya Pradesh. So same thing, like if you take a look at Jabalpur, almost which color green is that? I think it might be this one, 50 to 60% probably. So 50 to 60% houses are rural houses. Okay. So here what we are getting, the rural house percentage is really okay. So I think this is 40 to 50. So it's not 50. Ah, okay, it's not 50 to 60, it is 40, 30 to 40 or 40 to 50 anyway. Like I'm not able to discern the color. But anyway, like it's very less compared to that of Latur. So instead of the case in Latur, in this area, the percentage of rural houses were less. So almost same magnitude earthquake occurred in Jabalpur after the Latur earthquake, and there was hardly any casualty because the number of this rural houses were less in Jabalpur. So essentially, why we are talking about this earthquake and rural houses is that uh, This is like, you can use simple classification techniques like this equal interval one that has been used here, while like using the census data or something like that. And then we can identify the regions which are prone to earthquake risk. So that is what I'm trying to say. Like if you are staying in Jabalpur, you only know that okay, these many houses are there. But when you do some kind of GIS analysis, and you have a broader aspect, like you understand it in a broader way, then you understand okay why that much damage didn't happen in Jabalpur for the same magnitude earthquake that happened in Latur. So that is why GIS analysis and modeling, all this helps so that in future, if you have this data, then you know like which area is prone to the risk, and then you can actually help people out in terms of maybe rebuilding the houses or whatever it is. So such planning, long-term planning or broader planning can only be done when you have such uh, uh, a simple classification. So this is just a summary, like how much the rural population is there in Latur. Like we'll just focus on Latur and Jabalpur. So rural population is 79.6%. In Jabalpur, it is like 54.5. Urban population is less in Latur, but it's relatively more in Jabalpur. But then if you take a consideration of rural and urban, it's more or less like 50-50 in Jabalpur. And then rural houses are more in Latur, uh, and urban houses are less in Latur. So 79% or 80% like um, houses, rural houses in Latur led to the death of around like thousands of people in that area. But if that similar earthquake had happened in Khargon, even more number of people would have died because the rural house number is more in Khargon. Okay. So now we'll just discuss few questions that I had compiled. Like basically, it is the week five solutions that have been published, and just three questions which are related to week six lectures. So I'll just once again stop sharing the screen and share the uh, PPT. Okay, so this is okay. Yeah, map overlay operations are based on which of the following? Actually, I automatically showed the answer also, but yeah, still. We were doing this topic last session about overlay operations. So how, like using which of these do we do the map overlay operations? I think this was part of your week five assignment. And since the answers are published, I thought I'll discuss those. Okay, so the answer is Boolean logic. So if you remember, we were discussing about AND operation, OR operation, then what else? XOR, something like that, right? So that Boolean logic is used in order to do the map overlay operations. The intersection A intersection B of two sets A and B is the set that contains all elements of A that also belong to B. Is the statement right or wrong? Like false, no change, true, or none of the above? Like you have two sets A and B. Okay, okay. I don't think it's changing, right? One second, I'll share it once more. Now I think it will be visible. Yeah. So this is the statement. The intersection A intersection B of two sets A and B is the set that contains all elements of A that also belong to B. What is like, is this statement true, false, no change, none of the above? What is it? You can even try with the diagram, that Venn diagram, circles, and see if it is true or not. So the answer is true. And why is that so? Like if you take a look at this, like you have a circle. Let's, it's not a very good circle, but still, yeah, this is A and this is B. Now they're saying the intersection of A and B, which is basically this, okay, is the set that contains all elements of A that also belong to B, which is true. Like whatever is there in A that also belongs in B, that is the point which we consider as the intersection. So the statement is true. Which overlay operator has been used in the following figure? Oh, okay. Okay, so you hadn't given the answer. Okay, I was waiting for it. No, the answer is not A, because A means this, uh, what do you say? Whatever this coverage is, if it is AND coverage, then it should also be included in the output coverage. So that is not the case. In or also, like, it should have been a wholesome thing, but that is also not the case. This is basically, this B is basically erasing that portion in this input coverage. So this is basically a erase overlay feature, overlay operator, and not any of these and or not. So basically the erase tool will remove the areas from the input layer which overlaps the erase feature. Okay, so the output retains only those parts from the input which does not intersect with the erase feature. So this is basically used when you want to remove certain areas from the data set. Like if it's not of your requirement, you can just remove it, excluding specific regions from spatial analysis and all. Which is the raster based overlay operation. We had, I think, discussed these. It's basically all of them, like arithmetic operation, relational operation, conditional operation. They all come under raster based overlay operation. Which is neighborhood operation. This also, I think, we have discussed last time. At least the names we have discussed. Yeah, the answer is all of the above. Interpolation functions, topographic functions, search functions, they all belong to neighborhood operation. Evaluation of characteristics of an area surrounding a specific location is known as something which we just discussed. Yes, the answer is neighborhood operation. So in neighborhood operation, we always evaluate the area which is surrounding a specific location. That specific location, we would have all the details, and then based on that, we are evaluating the characteristic of the surrounding area. The procedure of estimating unknown values at unsampled sites using known values of existing observations is known as. This was from last time also, and the previous session also, I think we have discussed. Okay, so the answer, yeah, the answer is interpolation functions. Yeah, you're right. The dash of a surface can be represented in a digital elevation model. Like what out of these four do you find in a digital elevation model? Yes, the answer is topography. So you get information regarding the topography in a digital elevation model. Dash connect edges and facilitate navigation from one edge to another. This is about the network elements which we had discussed. Not really. It's basically junctions. Junctions are the ones that connect the edges. Turns are more or less like uh, restrictions. It's not basically connectors, but rather restrictions that are put into place in order to understand how that network is going. But it's an optional element. So the answer is junctions. Fleet management is based on, okay, I think I've not discussed this, but it's network analysis, but maybe I forgot to discuss it. I think I'll make a note of this and maybe we can discuss in the next session, or I'll see if I have any notes based on that. It's basically like I don't remember the technical definition of fleet management, but it's basically it involves optimizing the movement or operation of vehicles, like the delivery trucks that you have or taxis and all those things, using spatial data and network based algorithms. This is done in order to improve the efficiency or reduce cost and enhance service delivery. Like as I was saying, route optimization, like shortest path is better for delivery people. So such things, fleet management, when you do that, you will be able to identify the shortest path, or real time monitoring. Like you can see, right, if you're ordering some food or something, you can see where the rider has reached. So such things has been done using fleet management. This also I don't think I've discussed, but yeah, Dash is used in GIS, cartography, and remote sensing to generalize complexity in okay, this I've discussed. Generalize complexity in geospatial data. The answer is classification. As I was saying, like it reduces the complexity of any kind of uh, GIS data or in cartography. Cartography is basically related to map or remote sensing data, whatever it is. When you do the classification, it sort of generalizes and makes things easier for somebody needs who do not need too much information, just the basic ones. Okay, so that is all the questions that I have. And maybe in the next class, if your week 6 solutions are out, we'll discuss that. So with this, we come to the end of today's session. Thank you, and yeah, maybe in the next class, I'll make a note of it. Maybe I'll try to discuss about DGPS also. Okay, so I'm ending the meeting.